Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, Professor in the Chemistry Department of University of Delhi. Today, we are going to discuss about the module called Electrochemical Scanning Tunneling Microscopy, abbreviated as ECSTM, and we shall be talking about data analysis under the paper of Surface Analytical Techniques, Part 1. After completing this module, you should be able to understand what is adsorption of anions, adsorption and self-assembly of organic molecules, metal UPD and OPD, that means under potential deposition and over potential deposition, then single molecule charge transport and switching. Now, adsorption of anions is the first thing that comes to one's mind while talking about this. The study of adsorbates is of importance for electrochemistry as many reactions proceed through intermediate adsorption stages. Adsorption of self-assembly of organic molecules. The adsorption of cell assembly of organic molecules at metal surfaces comprise a growing field of interest for fundamental research as well as technologically important applications. This is due to the immense importance of organic molecules in applied areas such as additives in plating, baths, etc. Examples for superconformal growth in the demarcescence process of copper deposition or as corrosion inhibitors, which is a very wide area these days, and to the growing field of molecular nanotechnology for designing materials and functionalized surfaces with novel electronic, magnetic, photonic, mechanical, and sensing or diagnostic properties. We cannot study all this. Now, adsorption of organic molecules over surfaces, of course, the add layer structure and reactions at the solid electrode interfaces has been intensively investigated due to its importance in many physical chemistry and life processes areas. The emergence of electrochemical scanning tunneling microscopy provides a new opportunity to study this subject at the atomic and molecular level in aqueous solutions, which till date wasn't possible. The feature article, as I said, this wasn't possible by other techniques, and this is the one which has come to the help. The feature article summarizes some of the latest progress in ECSTM application for the understanding of the structure and reactions taking place at the solid-liquid interface. The adsorption of atoms and organic molecules is clearly revealed after you analyze this data, and the knowledge of the underlying molecule substrate and the intermolecular reactions governing the add layer formation on the surface is reduced. Sublately and spectroscopy at high magnification, if we are to interpret two spectacular images discussed earlier and would be done later also, that point to an important part of the future of the STM. It is necessary to refine our understanding of STM image or images as the case may be. The simple view that the images are topographic of surfaces has been sufficient so far. Interpretation becomes more difficult for atomic resolution images of surfaces with inequivalent atoms. Note that the trajectory of the tip over the surface depends not only on the topography of the surface but also on the types of atoms on the surfaces and the bias voltage which is used. Specifically, when the sample is negatively biased, switch in left position, the tip follows the dashed path and goes higher over the shaded atom than the positive once. The tip follows the dashed path and goes higher over the shaded atom. Then the positive samples bias voltage switch on right position when it follows the dot dashed path. The response would occur for an atom with an excess of electrons. When the tip is over such an atom, the turning current flows rarely from the atom to the excess of electrons to the tip, but not from the tip to the atom that does not rarely accept more electrons. Thus, current flows rarely when the sample is negative. Then the feedback network moves the tip away from the surfaces to reduce the current to the present value. Conversely, the current does not flow readily when the sample is positive. Then the feedback network moves the tip towards the sample to increase the current to the present value. We have been talking about this technique where we are carrying out the data analysis, metal UPD and OPD. The deposition of metal from aqueous solution has attracted the attention of electrochemists for more than over 100 years. This is related to the importance in many industrial scale processes such as plating and metal finishing. This underpotential deposition and overpotential deposition of metal has found a great deal of applications as far as the role of electrochemists are concerned, and this is being utilized in this technique very extensively. Contemporary frontiers in this field include, for example, the optimization of the electrochemical copper deposition in the fabrication of high quality nanometer wide integrated circuit interconnects. This is in terms of technical terms known as Damascene process. Single molecule charge transport and switching. An advanced application of electrochemical scanning tunneling microscopy for the study of electrochemically controlled electron transport phenomenon in single molecule junctions is described. As has been said, electrochemical scanning tunneling microscopy is very important as far as the terms of this kind are concerned. Fundamentals of scanning tunneling microscopy. We had already indicated in earlier slides that this STM, called scanning tunneling microscopy, is a very important technique used in electrochemical work related to many areas. One of the very important areas that is studied with the help of STM is pertaining to corrosion studies, wherein it is able to very categorically state that what are the materials which are present in the layer which are able to inhibit the corrosion of a system on the surface. Now, the origin and operation modes of this, when we talk about, we can find out about who started and what is the principle of this. The scanning tunneling microscope was developed by Binning, Roher, Gerber and Wiebel. Since STM can be used for imaging at atomic scale level, which is a very fine level of analysis, this belongs to the most powerful experimental techniques of the surface science. When we require analysis at an atomic scale level, STM is one of the best techniques that one can think of. So therefore, in STM what we do is a sharp metallic tip is placed very close to the surface and a small bias voltage is applied between the tip and the sample. As a result, a current of electrons, here it is written as IT, flows between the electrodes through the vacuum gap. This process is a quantum mechanical phenomenon and it is called as tunneling effect. The electrons tunnel through this electrically insulating layer, giving rise to a measurable current which displays an exponential dependence on the distance between the two conducting electrodes. As I said, with the help of this phenomenon, a very low, small sized particles at a level of atomic level, this technique can be used to assess that. Continuing this, we will find that electrochemistry is a very important area where STM is being very extensively used all over. So electrochemistry in scanning probe microscopy is a very important area. Basic concepts and applications when we talk about, that is in terms of studies of STM, we'll find that electrochemical scanning tunneling microscope was the first tool for the investigation of solid-liquid interfaces that allowed in situ real space imaging of the underlying electrode surfaces at atomic level. This is being highlighted again and again, that even up to atomic level we can very precisely analyze with the help of this ECSTM. Therefore, ECSTM gained much more importance and emerged as a prominent tool for the determination of the local surface structures as well as the dynamics of reactions as well as processes that take place at these surfaces in an electrolytic environment. Although the fundamentals of both techniques are then essentially the same, the two different elements must be introduced in a conventional STM setup in order to operate as an ECSTM, that is, the electrochemical scanning tunneling microscope. An electrochemical cell consisting of two working electrodes with a biopotentiostat approach and a suitable ECSTM probes are the ones which are put in use. Understanding electrochemical processes such as corrosion, deposition, and adsorption. When we talk of deposition, it could be the deposition of metals or, for that matter, any other organic or inorganic material. Electrochemical scanning tunneling microscopy has been utilized to study a variety of materials including copper, nickel, and iron in many different corrosion environments. Now this leads to pit formation, which can be studied with the help of this technique. On metal formation, this pit formation on metal also has been studied with the help of this. This diagram shows the scan which has been calculated when this kind of a phenomenon takes place. This has been shown on the right side of the slide. Now, as we said, it finds great number of applications in the area of corrosion, and when one looks at the kinds of corrosion that one comes across, you have a variety of corrosion forms, which includes electrochemical corrosion, uniform corrosion, crevice corrosion, filiform corrosion, pitting corrosion, intergranular corrosion. So all these can be studied with the help of this technique, but pitting corrosion, which is the most dangerous form of corrosion, takes place at passivated metal surfaces and leads to a creation and growth of an active pit. It is quite common that these pits can easily develop at the defective sites, on the passive film surface, on sharp edges, or sites where the oxide film is thinner. It also forms on the sides where the oxide film is damaged slightly, and that leads to the formation of pits. The essence of pitting process relies in its anodic nature, that is on metal dissolution reaction, as compared with a passivated cathodic region surrounding this. thus allowing the continuous flow of electrons to take place as far as this phenomenon is concerned. The pit formation is depicted in the above figure, where peaks indicate the pitting corrosion. Most metal will have passive layers present in or on a semiconductor or insulating electronic behavior, and thus it is expected to understand the initiation of the pitting corrosion processes, which requires or this requires to embed semiconductor phenomenon into an actual classical corrosion mechanisms. This mechanism was extremely difficult to study by other means, but with the help of this, it has been possible to understand the pitting corrosion detailed mechanism. Combined instruments for electrochemical scanning tunneling microscopy and scanning electrochemical microscopy, or as we briefly put it as ECM, uses an ultra micro electrode as a probe, and by other amperometric or potentiometrically utilized techniques to investigate the activity and or topography of an interface on a localized scale. The tip moves much longer distance than the tunneling distance and measures Faraday currents that results from an electron transfer reaction at UME, and several operational modes of ECSTM have been developed which allows the investigation of local chemical properties of interfaces. To study biomolecular interfaces, these are most important methods which can be utilized for this kind of analysis. The advantages when we use ECSTM technique. The advantages of electrochemically used STM, there are many advantages, and there are many versatile techniques such as scanning electrochemical microscopy, SECM as we call it, which is also a useful tool to analyze interfacial physico-chemical processes. The main reason of using ECSTM is to enable it to localize electrochemical reactivity areas only if this is accompanied by changes in sample topography. For example, for deposition, adsorption, or dissolution reactions. Parallel to the advance of ECSTM, scanning electrochemical microscopy was developed as a new tool for localized work. Electrochemical atomic force microscope. This is a similar technique, but here AFM component is the one which takes predominance over other. That is why it is called ECAFM, Electrochemical Atomic Force Microscope. The setup or the instrument as is there has been shown in this slide. This slide shows that it has liquid cell setup, then case study with in situ imaging and EC cell potential control setup, then metal deposition, variable pH and variable cell potential component. This has been given in the photograph in this slide. Now, when we talk about the outlook of this, one can understand what is the importance of STM and AFM in technology and biology. Both are very important sciences. For technology, both instruments should become useful tools for monitoring and evaluating critical manufacturing processes. In time, the hope that manipulative processes will be possible in the nanometer range with STMs or related scanning probes. It may also be realized that it is certainly worthy for further exploration. For biology, the picture is much less clear because of the complicated structures and the larger structures involved in the biological molecule. The recent upsurge of interest and applications of the STM in physics and engineering research is the result of a dramatic breakthrough in instrumentation. On 14th October 1988, and an innovation in the last few years, this instrumentation has taken a very long leap, very major stride in this area. But the interest in biological application has not been accompanied by a comparable advances in methods for preparing and examining the specimens. The biologist who seeks to exploit the potential of the STM faces many challenging obstacles before this instrument can be applied as a routine tool to generate information that is unavailable to others. More traditional microscopes, when you use, you don't get this kind of information. This is not to dampen the spirits of those who wish to try that, but just to be realistic, there is a large gulf, there is a large gap between the possibility and the payoffs of a successful practical application. Well, our interest in biological applications remains very high, obviously, because everybody is working on the biological systems these days. Whether the best successes will eventually come from STM or AFM or other scanning probes in future is yet to be seen. We think several obstacles deserve special mention in the hope that innovative solutions can be found to overcome them. First among these, at least for the STM, is the poor electron conductivity of most biological molecules, for without the ability to conduct electrons, there can be no image from electron tunneling. Occasional exception specimens may arise from time to time and offer hope, but they will be limited use unless they represent broadly applicable mechanisms. The application of the metals to make conductive coatings or replicas presently has limited usefulness. The obvious advantage over more conventional microscopes is that the STM can easily determine height or Z information in these samples. But the drawback is that a replica is not original structure, and it is not realistic to hope for resolution at the level of atom or small molecules with such methods. To date, we hope for resolution at the level of atoms or small molecules with such methods. To date, we know of no STM micrographs of biological molecules prepared by any method that approach the atom scale resolution that is possible with more ideal materials. That is why affirmative instruments such as AFM, which has already demonstrated atomic and molecular resolution images of non-conducting samples, are potentially so important. Many important opportunities remain for further advances in instruments design and specimen preparation. Among these are extending the scanning range of microscopes and incorporating XY translation stages to help locate an identified feature of interest. Second, further development of scanning probe microscopes designed to image soft nanoconductors. Thirdly, finding ways to anchor biological samples, make them mechanically stable, and control their orientations and distributions. Fourth, learning to recognize target features among populations by use of reliable markers. And fifth, avoiding artifacts caused by preparative methods, etc. Scanning probe microscopy is a young field that's still in the early stages of development and its applications. The advantages of obtaining high resolution information with virtually non-destructive probe has been and will continue to be appealing for biologists and others. We have covered only a few examples of recent applications. One important area we did not include is the study of dynamic processes such as corrosion. Perhaps the great potential for scanning probe microscopes in biology will go beyond and recording of static images as new probes are developed that may be capable of sensing different kinds of signals to reveal the dynamics of biological presence at the sub-micro level or sub-micron level to be precise. Characterization with ECSTM. When we put to certain applications or the uses of this technique, we find out that this has very many applications. And when we talk about understanding the electrochemical processes such as corrosion, this technique is of a great help. Applications of ECSTM in the field of corrosion have mainly focused on understanding about the mechanism of corrosion initiation and the process of inhibition. This includes the process of pitting initiation, surface dissolution, passive film formation, and the effect of inhibitors. The effect of inhibitors is studied by making use of this in terms of whether they are covering the active anodic side or active cathodic sides, either of the two or both of these, or whether there is a very thin film which is formed, we can make out with the help of this technique, or whether any pit is being initiated or not. That is another important area where this is being used. ECSTM has been utilized to study a variety of materials, including copper, nickel, and iron. In many different corrosion environments, it is being used, as I said. In general, the term corrosion stands for material deterioration or surface damage in a liquid environment. In fact, whenever corrosion takes place anywhere, it starts from the surface. And that's why the study of surfaces by any techniques assumes great importance. In the case of metals, it is basically a chemical electrochemical process that suggests an oxidation of a metal which transfer electrons to the electrolytic environment and undergoes a change of valence from 0 to a positive value. We continue with this application part. Normally, this initial process leads to a number of parallel electrochemical methods that result in material dissolution and or eventually formation of a secondary corrosion product. Basically, the metal corrosion process can be classified in two different forms. One is general corrosion that symbolizes these corrosion processes involving the entire surface area of the material, and the second one, localized corrosion, which mentions to a number of corrosion processes that are triggered at specific sites on the material surface. The presence of surface passive film prevents the metallic substrate from further oxidation. That is, the surface becomes passivated. These days, this passivated surface or passivated layer is known as resistive layer, which covers the surface. However, the passive state of a metal under certain conditions is susceptible to localized instabilities that prompt the corrosion of metal electrode through the local dissolution of the passive layer. This process is called as pitting corrosion. SECM, that is scanning electrochemical microscopy, the same acronym is used to describe the instrument. Scanning electron microscopy has developed into a powerful technique for quantitative investigations of interfacial physico-chemical processes in a wide variety of areas, as considered in several recent reviews. So students, having given you a lot on the data instrumentation, data analysis, let's summarize what have you understood from this module. Well, ECSTM plays an important role in clarifying the surface add structures and physical chemistry processes, which is pretty important. The adsorption and assembly of organic molecules at the solid-liquid interface is determined by the interplay between molecule-substrate interactions and intermolecule interactions. Adsorption orientation or structure of organic molecules on surfaces provides us rich information of the factors or about the factors which are governing the formation of add layers on the surfaces, which is invaluably important to control or to controllable construct complexes. ECSTM has imposed a huge impact on almost every field of solid-liquid research with rapid development in the past 20 years. The surface structure provides us a molecular level understanding of the structure at the solid-liquid interface, complemented by other information from supramolecular chemistry, organometallic chemistry, or surface chemistry, or electrochemistry as such, would really pose a bigger front for use of these equipments like ECSTM. Thank you so very much.